5.10 and 11 are about optimization problems. Basically, we are taking what we did in like 5. I want to say 5, where we did how to find absolute max or min values, and we are turning it into an application. So really, the tricky part of this is going to be coming up with the formula ahead of time, coming up with the equation that we will be using to then optimize, or in order to maximize or minimize. So I have some steps here. Okay, let me make this a little bigger here. The first step, if possible, is we draw a picture. A lot of times we will be using something like from geometry, so it's good to have a picture with labels if possible or necessary. Number 2, we define the variable to be optimized. I'm abbreviating that VTBO here. VTBO? I don't know. Anyway, define the variable to be optimized and then at least one other variable. Okay. Then we write an equation for our variable to be optimized in terms of one variable. Okay. In other words, we want to rewrite this as, I'm trying to maximize A, and now I need to define A in terms of one single other variable, meaning we might need to use some substitution or some other relationship to get to that. And that step, going like 2 into 3, that's the part of this that can maybe be tricky because it takes some problem solving. And then step number 4, this is where we do the stuff that we did in 5.5. Pretty sure it's 5.5. This is the candidate test, where we differentiate our function, find our critical points, plug the values into the original function, and then test to see, what's the highest, what's the lowest, whatever it is that we're looking for. Okay. All right. So this first example says an open-ended box is constructed by cutting 4 squares from the corners of a 9 by 24 foot sheet of cardboard and folding. Okay. We're trying to optimize the volume of the box. So we basically don't have a lid on our box. You have seen this problem in algebra context, in a algebra context before, just maybe not with calculus. It's new with calculus, but the idea is that we have a rectangle and then we're going to cut off 4 corners. Try and make these squares. We're going to cut these squares off of the corners, and then we'll fold along these lines. So these flaps on the sides, like not the part we cut off, but this part, fold up and make the sides of the box, and then it doesn't have a top. So this right here will line up against this piece right there, and that's how we get the sides of our box. Okay, so the original piece of cardboard is 9 by 24. Okay, so let's see if we can label this. This whole thing here is 9 feet, and then this whole thing here is 24 feet. And we are trying to, okay, so we want to define the variable to be optimized. We are trying to optimize the volume of the box. Now here, it says optimize. Usually it says maximize or minimize. But realistically, do we want to maximize the volume of the box or minimize the volume of the box? Well, the minimum volume would be 0. We just don't have a box, so we want to maximize. Okay, so we are trying to maximize, and I'm going to use V for volume. Volume of a box, this is a rectangular prism, is length, we'll use LWH, length times width times height, or base times width times height, doesn't matter. Okay, currently, so that's step 2. I've defined my variable to be optimized as volume equals length times width times height. But I want length, width, and height to be in terms of the same variable. Not V, but just the same variable. Okay, so let's go back to our picture here. Because I'm cutting off these squares, I know that this right here, this dotted piece, is going to be the side length of the box. And I'm going to label this as 9 minus 2x. It's 9 minus 2x because I'm cutting x. I'm cutting squares that are x by x off of each side. So I'm subtracting x here, subtracting x here. And then the vertical piece will be 24 minus 2x. And then what's the height of the box? X, because that's the amount that gets folded up. So I can then write this as 9 minus 2x times 24 minus 2x times x. Okay? So now it's in terms of a single variable, which is what we want. If you would like to leave it like this and kind of do product rule within product rule, you can. I'm going to go ahead and multiply things together so that I can just use the power rule. So this becomes, all right, so 9 times 24. is 216x, and then I've got minus 18 minus 48, but times x, so minus 66 x squared, and then plus 4x cubed. Okay, that's better. Step 4, I am now going to take my derivative, find the critical point, etc. So my derivative's 216 minus 132x plus 12x squared, and I am setting this equal to 0 and dividing. I'm going to divide everything by 12. I know that 12 goes into everything because this was 9 times 24, meaning if I divide it by 12, it's going to be 9 times 2, so 18. And then this was 66 times 2. 6 and 2 is 12, so that's 11. And 12x squared divided by 12 is x squared. Okay, all right, that factors, and I'll move the x to the front because I know people freak out when I put the variable at the end. Okay, so we end up with x minus 9, x minus 2. So x equals 2 and 9 are our critical points. Now let's go back and figure out what the volume is. Frequently here with optimization, we can actually eliminate one of the options right off the bat, and so we only have one possible one to test, or only one possible value, critical point left that's going to optimize our volume. And in this case, if I plug in 9 minus 18, I have a negative side length. So I know right off the bat, 9 is not going to work. 2 is the only other option. I technically didn't think about the endpoints of my interval. Really, the smallest amount I could cut off would be 0. The largest amount I could cut off would be 9/2. Both of those would give me a volume of 0. So my maximum volume is not going to be at either of those. Okay, so my maximum volume occurs at 2, but I need to know what that volume is because I am trying to optimize the volume. So I'm going to plug 2 back in. I'm going to come over here and do it. So I get V equals, and I'm going to plug into my factored form. So 9 minus 4 is 5. Times 24 minus 4 is 20, times 2 gives me 100 times 2, 200, and it is cubic feet. Okay, next problem. A right circular cylinder is inscribed in a right circular cone with a radius of 6 and an altitude of 18. No units here, so I don't need a unit on my answer. I'm looking for the dimensions of the cylinder that maximize its volume. Okay, so let's try and draw this. I'm going to start with my cone, and then I'm going to put a cylinder inside it. Okay, there we go. So I'm trying to find the dimensions of the cylinder, so I'm going to call this R and H, that will maximize the volume of that cylinder. And I know that the radius of the cone is 6, and the height is 18. Okay. So I'm trying to maximize the volume. So once again, trying to maximize V. Volume of a cylinder is pi r squared h, but I need another relationship between r and h so that I can get this in terms of one variable. So my variable to be optimized is V, which is defined as pi r squared h, but I'm trying to replace one of those in terms of the other. Okay, I do have a similar triangle situation going on here. Okay, and actually I have a couple of similar triangles, places where I could draw them. I'm going to look at this triangle and this triangle. Okay, they are similar. If I wanted to prove that, I have an angle congruent to itself by the reflexive property. I also have right angles here and here, so angle similarity is all I need. But I can write ratios. Let's see. So I can write ratios where let's do the bottom side. So I'm going to write R over 6 is equal to, and then the height of the upper triangle, this piece right here is 18 minus h, and then the whole thing is 18. So 18 minus h over 18. All right, let's reduce that. So we get 3r equals 18 minus h. So I can replace h with 18 minus 3r. Okay, so this becomes pi r squared times 18 minus 3r, which is the same thing as, I'm going to distribute. I'm also going to factor 3 out just because I can. So I'm going to write it as 3 pi times 6r squared minus r cubed. Okay. Yeah, I just pulled a 3 out because I'll leave that with the pi as a coefficient to deal with later. I'm not going to have to use product rule because 3 pi is a coefficient. Okay, so now I've got my variable v to be optimized defined in terms of a single variable r, so now I can differentiate. So v prime is equal to coefficient 3 pi, and then I have 12r minus 3r squared. To find my critical points, I'm going to set that equal to 0 and divide everything by 3 pi. Actually, I'm going to take another 3 out. And then I have r times 4 minus r equals 0. So r equals 0 or 4. Obviously, if the radius is 0, I don't have a cylinder. My volume would be 0, so I can't maximize there. So it's going to happen when the radius is equal to 4. Okay, now it does say find the dimensions, not the original volume, so I don't need to plug it back in here, but I do need to figure out what h is. So h is 18 minus 3 times 4, so 6. So my dimensions are 4, or let's clarify, radius equals 4 and height equals 6. And that will maximize my volume. Okay, for the next example, this one's a little bit different. This one says which point or points on the graph of y equals 4 minus x squared are closest to the point 0, 2. Okay, so let's go ahead and graph that. That's a parabola opening downward with a vertex at 0, 4. Okay, so I've got a height of 4 there. I also have x-intercepts at 2 and negative 2. So there's my parabola. Okay, so which points on these are closest to the point 0, 2? So 0, 2 is right here. And so really what we're talking about is we want to know how far away are any of the points, you know, and we could draw them anywhere, any of these points, how far are they from that point 0, 2? I'm going to call this point xy. Okay, so to define my variable to be optimized, which is going to be the distance, this distance right here, d, I'm going to write that I'm trying to minimize d equals, and then I'm doing distance formula between the point 0, 2, and then any point xy that's on that parabola. So x minus 0 squared is just x squared, and then plus y minus 2 squared. Okay, now I currently have two variables inside my definition equation for d. So I'm going to go back to my original equation, my original function that I graphed, and y is 4 minus x squared. So I can replace this y with 4 minus x squared, which gives me root x squared plus, and then 4 minus x squared minus 2 becomes 2 minus x squared. And then that whole quantity is squared itself. Okay, at this point, I have my variable to be optimized in terms of one variable, but I don't really like the chain rule within the chain rule within the chain rule actually again. So instead, what I'm going to do is I'm going to rewrite the whole thing by squaring both sides, and I'm going to write d squared equals, and then I can take this thing off. And so then I just have x squared plus 2 minus x squared squared, and you can expand that if you want to, or use chain rule, doesn't matter. Now I'm going to take the derivative of this with respect to x implicitly. So on the left, I'm going to have 2d times d prime equals 2x plus 2 times 2 minus x squared to the first times negative 2x. Okay, so combining that a little bit, it's going to be, let's see, so I'll have 2x. Actually, let's go ahead and divide everything by 2. Get rid of that 2. Get rid of that 2, get rid of that 2. Okay, so now I have x plus, nope, minus. So I'm distributing the negative 2x to this. So minus 4x plus 2x cubed. Okay, that's better. So then solving for d prime, I need to divide both sides by d. So I get d prime is equal to x minus 4x plus 2x cubed. Nope, actually, let's combine that. Negative 3x plus 2x cubed all over d, the original function d, which I'm going to go ahead and plug that back in. So x squared plus 2 minus x squared squared. Okay, there's my derivative, and it's not going to be quite as gross as it seems. So I'm setting that equal to 0. If I'm setting a fraction equal to 0, I need to know where the numerator equals 0. So I'm going to start just with my numerator equal to 0. I'm going to factor an x out of that and have x times, I'm going to put it in the other order too, 2x squared minus 3 equals 0. So x equals 0, or add 3, divide by 2, then take the square root. I actually get plus or minus root 3 halves. Okay, let's go back, check critical points can be where the derivative doesn't exist as well. So is there anywhere where my denominator equals 0? That's only going to be true if what's inside the radical equals 0, and that's impossible because I have something squared plus something squared. So unless both of those somethings are 0, which they can't be because this, if I put a 0 in here, then this is a 4. So there is nothing that would make my denominator 0, so this is the only stuff I need to worry about. Okay, so now going back to check, if I plug 0 into my original distance equation, I'm going to get that the distance equals root 0 squared plus 2 minus 0 squared, so root 4, which is 2, which I could also just count because that's this distance here. If I plug positive or negative root 3 over 2 in, then I get root 3 over 2 squared is 3 halves, plus 2 minus 3 halves is 1 half. 1 half squared is 1/4. 3 halves plus, so 6/4 plus 1/4 is 7/4. So it's root 7/4, which is root 7 over 2. Oops. Root 7 over 2. Okay. And so root 7 over 2, I'm comparing that to 2. Well, in order for them to be the same size, this would have to be 4 over 2, so it'd be root 16 over 2. Okay. Root 7 is definitely smaller than root 16, so this number is smaller than 2, meaning that the points when x equals positive or negative 3 halves are closer to the point 0.02 than any other points. So my question says which points. Okay, so I need to get my y coordinates as well. Okay, so I'm going to plug root 3 over 2 in for x, and so I get y equals 4 minus root 3 over 2 squared, which is just 3 halves. So 8 halves minus 3 halves is 5 halves. My ordered pairs are root 3 over 2 comma 5 halves and negative root 3 over 2 comma 5 halves. And those are my 2 closest points. For this last example here, we have 2 posts and that are 30 feet apart, and we have 2 wires going to a single stake. We're trying to use the least amount of wire. Okay, so we need a picture for this. So we have this can be the ground. Nope, that's not a very horizontal ground. All right, it's a little bit better. So we have a 12-foot post and a 28-foot post, and they are 30 feet apart. So this distance is 30 feet. This is 12. This is 28, not degrees. And we're putting a stake somewhere in the middle, okay, that will have 2 wires like this that will be attached to it. And also we can go ahead and safely assume that the stakes or the posts are perpendicular to the ground. So what we are trying to do is we are trying to figure out where should that stake go as far as distance between the, like from one to the other in order to use the least amount of wire. So we are trying to minimize the amount of wire. I'm going to use a capital W for the amount of wire. Okay. That amount of wire is going to be this wire plus this wire. Okay. I do see that those are both hypotenuses of right triangles. I don't know this distance. That's what I'm trying to solve for. So let's call this one X and let's call this 30 minus X. Okay. So then this amount of wire here is going to be, from the Pythagorean theorem, that's going to be the square root of 144 plus x squared. And this hypotenuse here, also from Pythagorean theorem, is going to be the square root of 28 squared, which is, let's see, 26 times 30 would be 782. So 784. Okay, 784 plus 30 minus x squared, which is going to be 900 minus 60x plus x squared. I went ahead and expanded that. Okay. All right. Well, got some gross chain rule stuff, but not too terrible. Okay. I am going to combine these two though and make that 1684. Okay. So let's take our derivative. So we have 1/2 times 144 plus x squared to the negative 1/2 times 2x plus 1/2 times that whole quantity, 1684 minus 60x plus x squared to the negative 1/2 times negative 60 plus 2x. And then what can I simplify? Let's see, I can cancel out a 2 here and a 2 here. So I now have x over root 144 plus x squared. And then here, I'm going to cancel a 2, make that a 30, make that an x. So I'm going to make this plus x minus 30 over root 1684 minus 60x plus x squared. So I'm setting this equal to 0. But I definitely don't want to try and solve that by hand. So here is that graph. And then I'm going to set that, or I'm going to calculate my, I'm going to calculate my 0. And I have already played with the window a little bit. I'm going 0 to 30 because I know that's my biggest x. And really, I should be checking the endpoints. We'll come back to that. And then my y value, I'm going from negative 1 to 1 because I just want to know where it crosses the x axis. So I'm going to do second, calculate 0 and negative positive values, and it comes out to give me, oh, I went too far. Wait, it comes out to be 9. Okay, so x equals 9 is my critical point. And technically, I need to think about the endpoints of my interval, my possible values for x. Really, I can't go to the left of 0, okay? So that would be past this stake, and to the right of 30. So really, my critical points, my critical point is 9, but I need to also think about what happens at 0 and 30. Using my calculator, again, and you can go ahead and test this, but I'm plugging 9, 0, and 30 into the original W function, and I end up with the minimum value for W being at x equals 9, and it comes out to be 50. Again, did that on a calculator. No, yeah, so the total minimum amount of wire is 50 feet, and we're placing it, right here at 9 feet from the left side, okay? So don't try and do that one by hand.